we're going to talk about the maximum and minimum values of functions. Finding these values is actually an ancient and crucial problem in mathematics. To find local extrema, people have developed many different numerical methods, which we usually call numerical optimization. Of course, we need computer programs to help us get these approximate solutions. But when it comes to finding global extrema, or global optimization, we still don't have an efficient numerical method to get the job done. Usually, the best we can do is prove that the probability of an algorithm converging to the global extremum is 1. And keep in mind, this concept of probability assumes the algorithm runs for an infinite number of iterations. Infinity is an abstract concept. Real-world computers can only run a finite number of times, even if that number is incredibly huge. In practice, the most widely applied area is minimizing error functions, basically finding their minimum values. Most of the AI models we use today, like large language models, are built on artificial neural networks. These networks simulate the human brain and have the ability to learn. The connection strength between neurons is captured by weights. The final outputs of a neural network are essentially predictions, and naturally, there is always an error between these predictions and the actual exact values. When you change the weights, the outputs change too. This means that we can write the network's output as a function of its weights. Consequently, we can define the error function as the gap between this weight function and the true value. If we look at this gap as an absolute error, it is just the absolute value of the difference between the weight function and the true value. So, the learning process of a neural network is really just about changing weights to minimize the error function. Through continuous learning and adjusting weights, the network coaxes its outputs closer and closer to the actual exact values. This weight-adjusting process, the learning process, is exactly the iterative process used in numerical optimization. However, since error functions based on absolute values are non-differentiable, we usually use the squared error instead, which is the square of the difference between the weight function and the true value. Minimizing this squared error is what we call the method of least squares. As you can see, understanding the minimum of a function is absolutely essential. It is the bedrock of building AI models. Let's first look at the extremum problem for functions of one variable. We say a function f has a local maximum at c if, near the point c, all the function values are less than or equal to f of c. By the same token, we say a function f has a local minimum at c if, near c, all the function values are greater than or equal to f of c. Both local maximums and local minimums can be broadly called local extrema. This theorem shows us that if a function f has a local extremum at c, either a local maximum or a local minimum, then the derivative at c must be 0, or it simply does not exist. Now, be careful. This theorem only goes one way. That means if the derivative at c is 0 or does not exist, it does not automatically mean that the function has a local extremum there. What this theorem actually tells us is that if we want to hunt for local extrema, the points where the derivative is 0 or does not exist are the best places to start looking. The points where the derivative of f at c is 0 or does not exist are what we call critical points or critical numbers. Now, let's find the extrema for this function. First, we get rid of the absolute value, which gives us the equations on the second line. Then we take the derivative to get the very last line. Because x equals -1 is a split point where the piece changes, we have to handle this point separately. For all other points, we can just differentiate directly, like you see on the last line. Now, let's look at the derivative of f at x equals -1. If we use the method we learned before to find the left and right derivatives, we will see they are not equal. This means that the derivative of f at x equals -1 does not exist. Since we are focusing on finding extrema today, we won't go through the whole step-by-step process of calculating those one-sided derivatives again. Now, because this derivative never equals 0, the only critical number is where the derivative does not exist, namely, at x equals -1. When x is less than -1, the derivative is -1, which is negative, so the function f is decreasing on the left side of -1. And when x is greater than -1, the derivative is 1, which is positive, meaning that the function f is increasing on the right side of -1. Therefore, this proves that the function f has a local minimum at x equals -1. This example shows that a critical number is not always an extremum. Looking at the equations on the second line, the split point happens at x equals 2. If we use the method we learned before to find the left and right derivatives, we will see they don't match, meaning that the derivative of f at x equals 2 does not exist. So, x equals 2 is indeed a critical number, and the function value there is f of 2 equals 1. However, because this function is strictly decreasing, f does not actually have a local extremum at x equals 2. This theorem shows us that if c is a critical number and the function f is continuous there, we can use the first derivative to tell whether we have a local minimum or a local maximum at c. The first scenario is for finding a local maximum. For f to have a local max at c, the function needs to be increasing just to the left of c and decreasing just to the right of c. This means that the first derivative is positive on the left side of c and negative on the right side of c. The second scenario is for finding a local minimum. For f to have a local min at c, the function needs to be decreasing just to the left of c and increasing just to the right of c. In other words, the first derivative is negative on the left side of c and positive on the right side of c. Now, the third scenario has two possibilities. If the first derivative is positive on both the left and right sides of c, it means that the function keeps increasing everywhere except right at c, so c cannot be a local extremum. Likewise, if the first derivative is negative on both the left and right sides of c, the function keeps decreasing everywhere except at c, which means it is not a local extremum either. Let's look at the function on the screen, which has a split point where the pieces meet at x equals 1. If we use the method we learned earlier to find the left and right derivatives, we will see that they are not equal. This means that the derivative of f at x equals 1 does not exist. So, x equals 1 is indeed a critical point. Now, let's try to use the theorem we just talked about. We want to check the sign of the first derivative to see if f has an extremum at x equals 1. It is easy to see that on the left side of 1, the first derivative is 2, which is positive, and on the right side of 1, the first derivative is -1, which is negative. Put another way, the function f is increasing on the left of 1 and decreasing on the right. So, you'd think f must have a local maximum at x equals 1, right? But actually, this conclusion is wrong. Look at the actual values. The function value at x equals 1 is 3, meaning f of 1 equals 3. But if you look at x equals 1.5, the function value is 3.5. This clearly shows that the function value f of 1 equals 3 is not the highest point around. So, is our theorem broken? Not at all. The catch here is that this function f is not continuous at x equals 1. It violates the prerequisite condition that the function must be continuous at point c. That is why we cannot use the theorem for this specific example, and it perfectly highlights just how crucial the continuity of a function really is. This theorem shows us how to use the second derivative to test for local extrema. Keep in mind that this test only works for critical numbers where the first derivative is 0. You cannot use it if the derivative does not exist. The rule of thumb here is simply to check the sign of the second derivative at point C. If the second derivative at C is positive, then the function f has a local minimum at C. If the second derivative at C is negative, then the function f has a local maximum at C. In this example, we want to find the extrema for the cubic polynomial on the screen. First, let's set the first derivative to 0, just like the equations at the end of the first line. Solving for x gives us the critical numbers x equals 2 and x equals -1. Since polynomials are always differentiable everywhere, we don't have to worry about any critical numbers where the derivative does not exist. Now, the first equation on the second line shows the second derivative. From the third line, we can see that when x equals 2, the second derivative is positive, so the function f has a local minimum at x equals 2. On the other hand, when x equals -1, the second derivative is negative, meaning that the function f has a local maximum at x equals -1. In this example, we are going to find the extrema for the function sine plus cosine. First, let's find where the first derivative is equal to 0, which you can see at the end of the second line. Then, the first equation on the third line gives us the second derivative. From there, we just check whether the second derivative is positive or negative at the critical numbers, and that will clearly give us the local extrema. This screen shows that if the function f is defined on an open interval or a union of open intervals, then all the critical numbers can only come from two places, where the first derivative is 0 or where it does not exist. There are simply no other critical numbers besides these. This screen shows that if the function f is not defined on an open interval but on other kinds of intervals instead, like the ones you see on the top two lines, then the endpoints count as critical numbers too. Put another way, for this type of function, we have three different sources for critical numbers, where the first derivative is 0, where the derivative does not exist, and the endpoints of the function's domain. This screen shows us that the endpoints of the domain can also give us extrema. That is why we specifically call them endpoint maximums and endpoint minimums. Let's assume that point C is an endpoint of the domain of function f. Here is how we define an endpoint maximum and an endpoint minimum. When we say a function f has an endpoint maximum at C, it means that f of c is the largest value nearby. So if c is a left endpoint, the nearby values can only come from the right side, meaning that x is greater than c and close to c, so f of x is less than or equal to f of c. But if c is a right endpoint, those nearby values can only come from the left side, where x is less than c and close to c, which means that f of x is still less than or equal to f of c. Similarly, when we say the function f has an endpoint minimum at c, it means that f of c is the smallest value nearby. If c is a left endpoint, we only look at values where x is greater than c and close to c, meaning that f of x is greater than or equal to f of c. And if c is a right endpoint, we only look at values where x is less than c and close to c, which means that f of x is also greater than or equal to f of c. This screen defines what we call the global maximum and global minimum. When we say a function f has a global maximum at D, it means that the function value f of D is greater than or equal to every other function value across its entire domain. On the flip side, saying the function f has a global minimum at D means that f of D is less than or equal to all other function values in the domain. As you can see on the very last line, this function involves an absolute value, and it is defined on a closed interval that is shown up on the second line. Once we get rid of the absolute value, the resulting function is what you see on that last line. To start off, let's take the first derivative of the function. The result is right here on the third line. Now, at the split point x equals 0, the derivative does not exist because if we calculate the left and right derivatives, we will find they don't match. So, x equals 0 is the first critical point. Next, let's look for where the first derivative is equal to 0. Looking at that same third line, we can see the derivative is 0 when x equals 1, which makes x equals 1 to be another critical point. Now, notice that the derivative also equals 0 at x equals -1. However, x equals -1 is not in the function's domain, so it does not count as a critical point. By definition, the endpoints -1/2 and 3/2 count as critical points too. Now we're going to use the first derivative to check for extrema. It is pretty easy to see that the first derivative is positive on the open interval from -1/2 to 0, and also on the open interval from 1 to 3/2. On the other hand, it is negative on the open interval from 0 to 1. This tells us that the function f is increasing on the open interval from -1/2 to 0, and the open interval from 1 to 3/2, and decreasing on the open interval from 0 to 1. By applying the theorem we discussed earlier, we can classify the extrema for these 4 critical points, just like you see on the screen. To find the global minimum, we simply look at all these different types of minimums and pick the absolute smallest one. Similarly, to find the global maximum, we look at all these different types of maximums and pick the absolute largest one. The function on the second line is defined on the closed interval from 0 to 2 pi. This means that the endpoints 0 and 2 pi both count as critical numbers. And if you look at the very last line, that is where its first derivative is shown. By solving for where the first derivative equals 0, we get 4 critical numbers, just like you see here on the screen. Moving on, it is pretty easy to see that the first derivative is positive on the open interval from 0 to pi/6, the open interval from pi/2 to 5 pi/6, and the open interval from 3 pi/2 to 2 pi. On the other hand, it is negative on the open interval from pi/6 to pi/2, and the open interval from 5 pi/6 to 3 pi/2. This tells us that the function f is increasing on the open interval from 0 to pi/6, the open interval from pi/2 to 5 pi/6, and the open interval from 3 pi/2 to 2 pi, and decreasing on the open interval from pi/6 to pi/2, and the open interval from 5 pi/6 to 3 pi/2. By applying the theorem we discussed earlier, we can classify the extrema for these 6 critical points, just like you see on the screen. Lastly, if we compare these different types of maximums, we can see that the function f reaches its global maximum of 1/4 at 2 places x equals pi/6 and x equals 5 pi/6. And by comparing the different minimums, we find that the function f has a global minimum of -2 at x equals 3 pi/2.